Welcome to the Human Factors and Ergonomics Hub, a series of educational podcasts that showcase the connection between human capabilities and good work design, brought to you by the Human Factors and Ergonomics Society of Australia.
Hello, and welcome to the HFE Hub podcast. My name's Gemma Read, and I'm filling in for Sharon Todd for this episode. She's currently taking a very well-deserved break. I'm a researcher at the University of the Sunshine Coast and director of the Centre for Human Factors and Sociotechnical Systems. And today I'll be interviewing Samantha Jackson. Sam is a registered psychologist, human factors professional, and PhD candidate within our research centre. She holds a Bachelor of Arts Psychology and fourth-year honours in Psychology and a Postgraduate Certificate in Safety and Accident Investigation. She has a background in the Australian Army and, as I mentioned, is currently pursuing her PhD at the University of the Sunshine Coast. Her research aims to enhance the safety performance of remotely piloted aircraft systems, which we usually refer to as RPAS. So today we'll focus our discussion on one of her recent studies, which has been published in the journal Applied Ergonomics. We'll see if we can provide a link to it with the podcast, or if you want to go ahead and search for it, you should be able to find it open access. The title is Flying Uncharted Skies, Unravelling the Network of Contributory Factors to Adverse Australian RPAS Events with an Aggregate Aximap. So first of all, Sam, welcome to the podcast. And I wondered if you wanted to start by just talking a little bit more about your background, your career, and how you came into the human factors field.
Hi, Gemma. Thank you. And thanks for the intro. It's really good to be here. As you mentioned, I have a background in the military where I spent 24 years in the Australian Army. The first half of that was with the Corps of Signals, so the branch responsible for communications and information systems. So think computers, radios, satellites, effectively about technology and information networks. And while in Signals, I completed my psych degrees, so I did those part-time while I worked full-time. And what initially drew me to psychology was a curiosity about why people behave as they do. And looking back now, I realise I was already starting to think in systems, so interested in the broader factors that shape human behaviour and decision-making. After honours, I transferred into the Army Psych Corps, where I worked as a registered psychologist. My early roles were mostly health-focused, so I worked in clinical and organisational roles as well as operational psych policy. And during my time in Psych Corps, I was really fortunate to have some incredible bosses and mentors who had a significant impact on me. So Colonel Laura Sinclair was the first person to really take an interest in me, and she encouraged me to go into human factors and aviation psych within Army Aviation. So being the good young officer that I was, I went off to Aviation Psych, where I worked for Colonel Martin Levy, and Martin really took me under his wing there, helped me to grow in that space. And he had an extensive background in human factors, aviation psych, and was really generous in sharing his knowledge and networks. So I found that I found my place in Army Aviation. I spent the last 5 years of my service there and worked with crewed and uncrewed systems. We worked on various topics like safety management, accident analysis, job selection, broader human performance topics was super interesting. And I really loved it. And it was a really great mix of working directly with people in a system and also looking at the structures around them. And during that time at a conference, I met you and Paul Salmon, and you were talking about systems and human factors. And for me, I guess that was the last piece of the puzzle. I really found a way to bring all those things I love together. So working with people, complex systems, strategic thinking, and really a touch of blue sky futurism, which is exciting for me. So that was it. I was all into human factors.
That's great. Thanks, Sam. And I think that really reminds us of the importance of mentors and the role that we play in encouraging, maybe junior people in our areas to really get into human factors. So that's a really great story. I guess kind of going on from there, so what made you interested in pursuing a PhD, and why then did you choose to look into RPAS safety?
Good question. I always thought that I would go into a master's degree in one of the specialty areas of psych, fairly traditional approach in psych in Australia. But when I did my honours, surprisingly, I found that the part I loved the most was the thesis component. I really loved reading through the literature and identifying the gaps and thinking about the problem and how we might approach it, and even working through some of the problems usually presented by the stats analysis and interpretation. So that was, and, working through all that and then getting, really good marks was a bit of a dopamine hit for me. I just loved it. And I felt from that, I really wanted to go into research of some form, that problem solving that was associated with a PhD. And why RPAS safety? As you said, RPAS, remotely piloted aircraft systems, also called drones, UAVs. While the use of pilotless aircraft or vehicles is not new, the use of modern versions of this technology is really exploding. And I like to think of myself as a bit of a futurist. In particular, I like thinking about how humans will work with advanced technology and complex systems. And after doing that postgrad at Cranfield in safety and accident analysis, working with you and Paul, and my experience in Army aviation, I started to see some gaps in that rapidly expanding RPAS landscape, and in particular its integration into existing systems like the existing airspace. And that really presented an interesting problem, an interesting challenge that I found was quite exciting. And there's some incredible opportunities in this area that this technology can bring, but also some challenges to be worked through, and particularly in that safety space. And I hope that I can contribute to that.
Yeah, that's great. It seems like a way to kind of bring a lot of your background areas together as well, which is fantastic. Can you tell us a little bit about RPAS operations in Australia currently and where we're sort of currently at? Maybe some examples of context that the technologies are being used in at the moment, and maybe a bit about some of the risks that we do face with these technologies.
Absolutely. So in Australia, like in many parts of the world, as I said, RPAS is really growing quickly. A recent report by, I think it's pronounced Skyn Advisory on behalf of Air Services Australia, they released a report in February last year, and they forecasted that commercial drone flights are going to increase by 20% every year for the next 2 decades. So that means by 2043, they expect there to be around 60 million drone flights a year, which is incredible when you think about it. And last year, Pip Spence, who's the CEO and Director of Aviation Safety at CASA, she highlighted in a speech that now there is more commercial remote pilots than there is traditional pilots or conventional pilots. She used the term legacy pilots, which I found interesting, because I think that language really refers to something in the past. So it really suggests that we're on the brink of a major shift in what the future of aviation looks like. And right now in Australia, they're being used across so many different industries. We're seeing them in agriculture, mining, emergency services, logistics, surveying. In Queensland, in certain parts of Queensland, there's drone delivery service now, dropping off food, groceries, medical supplies. They've also been used in coastal land surveillance, search and rescue, wildlife monitoring, herding cattle, spraying. It's really exciting and so diverse. And the next evolution of uncrewed systems or remotely piloted systems is advanced air mobility, or AAM. That's where electric vertical takeoff and landing aircraft, or eVTOLs, will come into play. And so think of something about the size of a small helicopter, and they will transport people and larger cargo. And it's really not that far away. The safety framework's being developed around that. There's still a bit of work. But But look, with these opportunities comes a lot of risks. And I think one of the biggest risks is the speed of technological development. So while there are a lot of similarities with traditional aviation, RPAS systems do differ in important ways. We can't necessarily just plug and play. We can't plug them into the existing system. So as the name suggests, the RPAS, the people are working remotely in these systems. They are often geographically dispersed, or the crew within the systems are dispersed, so they don't necessarily have the same environmental cues as someone sitting in a cockpit. They don't necessarily have the same methods of communication. So, and also as we push out into what is known as beyond visual line of sight, so where the RPAs are being flown beyond the pilot's vision, it really adds another level of complexity and risk. So how communication, situational awareness, decision making all happens is different in these environments. So the system, as I said, it's developing, and it's CASA are really leaning forward into this development and working with industry, but there's still a lot of work to do. It's a difficult process to create these systems surrounding this technology. It's complex with lots of dynamic elements, so that takes time and is challenging, but there's lots of opportunities associated with that.
Yeah, sounds perfect for a PhD topic. So let's focus a little bit on your recent study, which involved analysing a set of RPAS incidents that had been investigated by the Australian Transport Safety Bureau, so the ATSB. I should probably note that I'm actually one of the authors on the paper, so I'm probably asking some of these questions a little bit more for the listeners than for myself. But could you tell us a bit about the motivation behind the study? So, why you set out to do this accident analysis and what you were hoping to find out.
Yeah, sure. So in the most recent paper, we applied aggregate AxiMap to analyse 14 RPAS events that had been investigated by the ATSB. So we chose accident investigation reports as they give us a really rich source of feedback, telling us how the system's functioning. And that can give us some insight into how systems are behaving under pressure, which is really useful information to optimise, or to help us optimise the systems. The AxiMap allowed us to take an in-depth look at each of these events. And so from this, we had hoped to see some important indications in the system that signalled areas for improvement and also areas that are functioning well. All of that is important in optimising systems, that information. So then by aggregating the AxiMap data from these events, we aimed to identify patterns that showed systemic contributing factors across the 14 incidents. We can't generalise it across the system in its entirety because the number was only 14 reports, but still we got some important information. So we looked at systemic contributing factors across those, or we hope to. And this enables us to identify the gaps and the shortfalls for further targeted intervention.
Yeah, great. You touched on this a little bit already, but can you tell us a bit about how you went about the study and maybe give an example of one of the incidents that you analysed?
Yeah, so I won't go into really detail. You can read the article if you want all the nitty gritty, but really we're using specific criteria. We did a structured search of the ATSB's National Aviation Occurrence Database, which is online, and that's where there's a lot of information about safety occurrences in varying detail depending on how they were investigated, how in depth. So after applying that, we ended up with 14 reports. And then the aggregate AxiMap was constructed in two stages. The first, we reviewed each of the reports in detail, and we identified actors and organisations in the report that played a part in the incident, and we mapped those in an actor map. And then looking at the report, we identified contributory factors that played a role in the incident causation. We mapped these in the AxiMap in a flow of event sequence so we could see roughly the timeline of the events with the contributing factors, and then identified relationships between the contributing factors. We did that for each of the 14 reports. And then the second stage, we applied the AxiMap classification scheme, which was developed by Paul Salmon and colleagues, to each of the AxiMaps. And this was practically done by taking each of the contributing factors and then classifying it against, I think there were 79 thematic contributing factors, which enabled us to see patterns of recurring causal links across the incidents. And examples of one of the incidents that we looked at, there were lots of interesting, all of the cases presented interesting background circumstances, but probably one of the most from a systems human factors perspective with potential leverage points for improving system safety, I think, was an incident involving the loss of control of during taxi of an RPA at Bruhl Airfield in 2020. So really quickly what happened was they had conducted maintenance on the aircraft. They were conducting test flights after, which is fairly standard. And then after a successful flight, the aircraft was in the ground. The pilot started taxiing it towards the hangar. And in that process, disengaged the automatic mode and engaged thrust. But then when the pilot tried to reduce the engine thrust, the RPA didn't respond. And the pilot had to take action and direct the aircraft away from some bystanders that were standing close to the taxi area, and then directed it into a fence. So in the accident, it'd be really easy to stop if you're looking at the contributing factors at the fact that after the technical incident occurred, that being the engine not being able to reduce the engine thrust. But actually the report thankfully provided a lot of information about other interacting factors. So we saw things like a rapid development of the RPA. We saw evolving changes. So after that changes to the technical function of the aircraft, manuals were not updated. There were ongoing technical challenges, so the technical problems, thrust not being able to be reduced. There was configuration of the handhold controller presented challenges. There were evolving regulations at the time and policies relating to fatigue. There was a high tempo operational schedules, sunny, warm conditions, inadequate sleeping accommodation. There were dual roles allocated to the chief remote pilot, who was managing the flight, but also responsible for managing fatigue, monitoring it. So there was, and also there was geographic dispersion between crew members. So it made it difficult to access flight termination systems. So we can see from that report, just that report, that there were many systemic contributing factors. And the AxiMap allowed us to see some things that went wrong, but also things went right. So something that comes to mind is that the pilot was able to intervene with the aircraft that was heading towards the bystanders and send it off into another direction. So that meant that while there was damage inflicted to the aircraft, it was reduced. The risk was reduced in that it didn't hit anybody and hurt anybody else. So that's interesting.
Yeah, that's a really, really interesting example. And as you say, that's just one incident in your 14. So can you tell us a little bit about, once you aggregated all of those incidents together, what were some of the key findings of the study?
So from those 14 AxiMaps, we found 232 contributing factors across the 5 of the 6 AxiMap levels. We were able to classify those into 31 thematic contributing factors using the classification scheme. Most of the thematic contributory factors were found at the 2 lowest levels of the hierarchy. And so the themes that stood out there were activity, work and operations, compliance with procedures, violations and unsafe acts. And the third one was equipment, technology and resources. And we also looked at network metrics. So we examined the strength and the frequency of relationships between the contributing factors. So this allowed us to see how well these contributing factors were connected to another node in the network. So, for example, a node that had lots of connections coming into it it showed that it was more influenced by other nodes in the network and other contributing factors, and nodes or contributing factors that had networks going out a lot showed that it was more influential on other contributing factors. So these offer potential leverage points in the system for us to tackle if we want to improve safety. So what did it tell us really in clear language? So really it reinforced what we already knew from systems thinking, that adverse events don't happen in isolation. They really emerge from a combination of actions and decisions across the system. So it was nice to see that. But while this holds true, we really did see a lot of gaps at the upper levels of the system. So that means that really there was limited or no references to higher factors being investigated really in the accident report. So that was as a result of the sources that we looked at. And we recognise there are lots of reasons why investigations don't always examine those higher level contributory factors, like, not enough time or money or expertise necessarily. But the implication really is that the depth of those systemic factors that can be identified are limited, so thus potentially stronger leverage points are not always identified. We also found really the central role and the tightly coupled nature of equipment and technology in the system, which is probably not surprising given the fast pace that we see that technology is being developed and how new it is. It was highly influential on other nodes and it was highly influenced by other nodes. But interestingly, it was also, it connected to itself a lot, suggesting that there could be a cascading sequence of technological failures, which highlighted that tightly coupled nature of the technology in the system. But really what's important to note is while there was lots of connections with equipment, it's not the only factor. There were lots of other system factors that played a part, environmental and equipment design, policy and procedures, they all played a part as well. And we also saw a major theme was compliance with procedures, violations and unsafe acts. So things like errors that might occur. So when setting up, sometimes technical safety indicators were missed, or non-compliance with policies or procedures. So that might have seen that in terms of mishandling of aircraft. So it's not being transported correctly, which might create damage to the aircraft. So these are also areas that we identified as important factors.
Yeah, thanks, Sam. That's really comprehensive overview. I think it's quite interesting what you mentioned about, the kind of lower level factors versus the higher level factors. And we probably haven't quite, for those listeners who aren't familiar with the sort of AXIMAP framework, it sort of shows a hierarchy of contributory factors from the bottom being the kind of environment and the equipment being used through to the people involved in the event, all the way up to sort of local management and then regulators and governments. So the higher levels are kind of your policy, public policy decision making, regulation and things like that. And I suppose, you make a good point that it can be quite hard to investigate things at those higher levels. I think often, those decisions are made many years prior, and it can be hard to create those kind of causal links down to the accident itself, where it's often much clearer to sort of see those technical issues or those non-compliances with procedures, on the day. Often a lot easier to kind of investigate those factors. So we tend to see them come through, don't we, in a few different areas. So really, really interesting, and I think really nice to see this, the AXIMAP analysis done in the RPAS space. I think it was the first application of AXIMAP to this particular area. Do you know that one?
Yeah, I think it was the first. It was definitely the first AXIMAP, and it was definitely the first aggregate AXIMAP. So, and we, as a part of the paper in the supplementary material, we included all of the AXIMAPs for each of the investigations that we reviewed, so people can see those if they want to have a look at the AXI maps in more detail as well.
Yeah, and it's interesting to have a sort of Australian sample of accidents or incidents, and it'd be interesting to see, how that looks internationally as well, if people are looking in other countries. Look, that's a fantastic summary of that study, Sam, and I do encourage listeners to have a look for the paper as well if you're interested. But I guess going on from there, so based on your research and the reading that you've done in the area so far, what would you say are some of the key challenges around RPAS safety?
So I think that this study in particular and the work we've done since, which we might talk about soon, I really think it really highlights the complex and tightly coupled nature of RPAS. It really is a system that operates in a highly dynamic environment. There's so many advancements in technology and policy and applications of that technology occurring. I mean, if you're following the news cycles, you're seeing advances and news coming out about these. They're coming out every day. So there's all these changes quickly occurring. And look, there are many elements that contribute to safe conditions within a system. As you know, these come from both within the sociotechnical safety system and also from external pressures. And I don't think we necessarily have a clear picture of what that looks like at the moment, or all the elements to that, because it's changing so quickly. And so if we don't know what that looks like, our ability to manage the system effectively is impaired from my perspective. And I think that there are numerous challenges in understanding the mechanisms of controls and feedback within the system, and also ensuring that our feedback loops and our ability to respond to those are agile and flexible enough to keep pace with that, the evolving technology.
You've guessed my next question, Sam. I think you started to talk a little bit about where your research is going next. So let's hear what's next for your PhD research.
So we've just finished the main data collection for the next phase of this project. In this phase, we use Nancy Levison's STAMP control structure to model the optimal socio-technical safety management system for RPAS operations in Australia. So that was, we drafted that from a number of high-level documents from ICAO, CASA, JARIS. These are all stakeholders that sit at the high level of the system that Gemma was referring to before. And so we drafted the STAMP model from those, and what they say a safety system should look like, all the components that it should have. And then we had SMEs provide feedback on the model. So we're now finalising and updating the model with their feedback. The next part of this phase is to get the SMEs to rate the maturity of that model. So then we can start to see if there's a difference between what the optimal model is and where we currently are. And the last phase of this project will be happening later this year. And we're going to apply cognitive work analysis. Some of the listeners might be familiar with that, I'm sure. And we will use that to identify how stakeholders can move the system from where we are now to where we want to be in the optimal state. And the plan will be to finish everything up, hopefully next year, with some broad recommendations about the Australian RPAS safety management system, and also looking at how we use human factors methods in that many models approach, because we've applied several models over this project. So how we use that to address complex issues. So hopefully that will provide some insights for people interested in human factors methods.
Thanks very much, Sam. That's a really fantastic overview of your research and, what you've done so far and where you're going. Hope people found that really interesting. It's definitely an interesting project for me to be involved in, and it's great research that hopefully will have some real positive safety benefits as well. So thank you, everyone, for listening in, and thank you again, Sam.
Thanks, Gemma.
Thanks for joining us at the Human Factors and Ergonomics Hub, brought to you by the Human Factors and Ergonomics Society of Australia, where human-centred design really matters. If you like this podcast, make us your favourite in your podcast app. We look forward to chatting with you next time.